Okay, this is where we started last time.
Doctor?
Yes, I'm listening.
Excuse me, before we start, we sent an email last night about the quiz. We can delay it to Monday, tomorrow. Do you hear me, Doctor?
And in the WhatsApp group, Doctor, all the students in the WhatsApp group agreed.
Doctor, we don't hear you.
Assalamu alaikum.
Walaikum salam.
Alaikum salam.
So I'm back. Let me share the screen. Something happened, so that kicked me out. Now you see the OneNote screen.
Yes.
Okay, someone was saying something.
Yes, it's me, Doctor. I sent you an email last night talking about if we can delay the quiz to Monday.
Okay, listen, Shabab, everyone. See, I cannot change if something is set. I cannot change it if something is set, already set. I cannot change unless each and every student is agreed. So if you write, if one person write me email or two person write me email, don't expect that I can change this one. Because you may have a problem today, but there are some other students who may have problem tomorrow. So yeah, Shabab, if everyone is listening, and this is being recorded, if later you blame me for something, I have this in recording, okay? So tell me, if anyone has a problem to postpone the quiz for tomorrow, raise his hand. I can postpone the quiz for tomorrow. If you have any issue, raise your hand, please. Anji. ਉਹ ਯਾਰ ਉਹ ਆਫਰ ਤੇ ਮੈਂ ਕਰਾ ਦੇਣਾ ਵਾ ਹੁਣ ਤੂੰ ਸਬਰ ਕਰਨਾ ਜ਼ਰਾ ਫਿਰ ਮੈਂ ਟੀਚਿੰਗ ਦੇ ਵਿੱਚ ਹਾਂ
Doctor, are you speaking? Because your microphone is muted.
Yeah, I was waiting for your hand to be raised. Yeah, Shabab, anyone raise your hand if you have any problem to postpone this quiz till tomorrow. Okay, just give me a second. डाटा में करा देता है 1 GB 1 महीने ਲਈ ਉਹ ਕਿਸੇ ਨੂੰ ਕਹਿ ਕਿ ਮੇਰੀ ਲਿਮਟ ਜ਼ਿਆਦਾ ਕਰ ਦੇ okay so no one is raising his hand. We will have quiz tomorrow at the same time. All right,
Thank you, doctor.
Thank you, doctor.
you're welcome.
Thank you very much, Doctor.
Okay, so here is, you see the screen, we have del operator. Del operator, the first one is in Cartesian coordinates. Del operator in, let me also write in here. In Cartesian coordinates, then del operator in cylindrical coordinates, and del operator, as I have told you before, that del operator give us so many things. It give us a divergence. It give us gradient. It gives us what you call it, curl. It gives us the what is else, Shabab? Laplacian. It gives us Laplacian. Okay. Now, just to save my time, let me do copy and paste these things. Okay. The gradient of a field in since we are doing the cylindrical coordinates. So here, del operator in cylindrical coordinates. First thing here is the gradient of a field V in cylindrical coordinates. Del V is partial V by partial rho A rho, 1 over rho partial V by partial phi A phi, plus 1 over partial V by partial Z A Z. This is the gradient. Okay. Then what is divergence in spherical coordinates? In cylindrical coordinates, sorry, because we are in cylindrical coordinates. Now here I'm showing you what is this divergence in cylindrical coordinates. What is divergence in cylindrical coordinates is given here. And you know, I am copy and pasting this thing from the formula sheet, which I will give you in the midterm exam. I have prepared a formula sheet, and this is copy and paste from the formula sheet. Okay. So these things, they will be provided to you. So divergence, this is divergence of a vector field in the cylindrical coordinates. And then what else we have is the curl of a vector field in cylindrical coordinates. This is curl of a vector field in cylindrical coordinates. So we have these three definitions, these three formulas: gradient of a scalar field, divergence of a vector field, curl of a vector field. Okay. Here, what is a scalar field? V is equal to V is a function of rho, phi, and z. It is not a vector field. It is a scalar field. Rho is a, V is a function of rho, phi, z in cylindrical coordinates. And that is why here I'm using V, and in the divergence and curl I'm using G.
Doctor?
Yes?
Can you repeat the V, please?
V is a scalar field.
So
A
in the
scalar
quiz,
function,
it
any
doesn't-
function of a rho, phi, z. But this G is a vector field. This G, what we are using in divergence and curl, is a vector field. It has three components. Okay. Then one more application of Laplacian of this del operator is this Laplacian. This is called Laplace equation. This is Laplacian. And here Laplacian is also for a scalar field. I do not need to write again and again what is a scalar field and what is a vector field, because a scalar field without the unit vectors, yani not a vector field, a scalar.
Doctor?
Yes.
We don't see the Laplacian.
Now you see the Laplacian.
Yes.
Good. So here are four things. Gradient. You are seeing four things: gradient, gradient of a scalar field, divergence of a vector field, curl of a vector field, and Laplacian of a scalar field. So you notice here that gradient of a scalar field is a vector field. Divergence of a vector field is a scalar field. Scalar field mean in divergence on the right hand side, no unit vectors. But when you see curl of a vector field, it is given by this determinant. So it is a vector field. And Laplacian of a scalar field is also a scalar quantity. And remember, if we put this Laplacian equal to 0, this is called Laplace equation. Laplace equation. But no, it is simply called Laplacian. So this is Laplacian in cylindrical coordinates. Similarly, we can write here Laplacian in these Cartesian coordinates. So here Laplacian in this number 4. Laplacian, that is del square V, which is equal to partial 2V by partial x square plus partial 2V by partial y square plus partial 2V by partial z square. So we have 4 quantities: gradient, divergence, curl, Laplacian. Here is also gradient, then divergence, then curl, and then Laplacian. Now, next thing is del operator in spherical coordinates. Del operator in spherical coordinates. Okay, what is the del operator in spherical coordinates? Let us see now. One thing is I simply say, okay, this is the del operator in spherical coordinates. Now apply this on scalar field or vector field, and you will get the answer. What answer? What is the gradient? What is the divergence? What is the curl? And so on. Now, if you simply want to see what is the only del operator in spherical coordinates, that is this one, just the del operator. Del operator in spherical coordinates is AR partial over partial R plus A theta 1 over R partial by partial theta plus A phi 1 over R sine theta and partial over partial phi. Now, when we apply this operator, we get gradient, divergence, curl, and vector, this Laplacian. So this is simply del operator. And if you simply ask what is the Laplacian, what is this del operator in what are the other coordinates? What is the del operator here in these coordinates? So this partial over partial x and this one we do not need to write here. Here I'm writing what are these coordinates, and okay, so here I have pasted what is del operator. So rho equal to this one, and also you know in cylindrical coordinates x is equal to rho cosine phi, y is equal to rho sine phi, and z equal to z. This is just for your say memory. And this is the del operator. And do you remember what are the these say coordinates, relation between these coordinates in spherical and Cartesian? Let me put that also here, just for you to remember here. You see, these are the relation or transformation equations. X equal to r sine theta cosine phi, y equal to r sine theta sine phi, z equal to r cosine theta. From spherical to Cartesian, and the other three equations, r square equal to x square plus y square plus z square. If you have x, y, z, you get r. Once you have r, you can get cosine theta equal to z over r and tan phi equal to y over x. Okay. Now, what are these three quantities? Actually, four quantities. Number one is the gradient. Okay. The gradient. What is gradient in this spherical coordinates? What is gradient in spherical coordinates? It is here. This is the gradient. And number two is what is number two?
Divergence.
Exactly. Divergence. So this is the divergence. I do not need to write again and again their name. Del V is gradient. Del V is gradient. And del dot V or del dot G, del dot G is what? With the dot product, it is divergence. And next quantity we have is what? In spherical, what is the next quantity? The curl. The curl of a what field? The curl of a vector field.
We can't see what you write.
Curl of a vector field. So next thing is this one, del cross G. So this is how curl of a vector field is defined. So this is curl, gradient, divergence, and curl. And the last thing is Laplacian. And Laplacian of a vector field number 4, quantity number 4. And from where I'm copying and pasting this is the formula sheet I have prepared for you. I'm bringing this from the formula sheet. So these are four say quantities, four type of these quantities: del V, del dot V, del dot G, vector, del dot G. Of course, dot product and cross product is for vectors. And again here del square V, no dot, no cross, so it is for scalar. And this is Laplacian. Okay. Next, one can ask teacher, okay, give us some examples. Okay. Examples. There are solved examples given in your book. Example 3.3 is find the gradient of the following scalar fields. Find the gradient of the following scalar fields. So what you have to do is to apply these formulas. For example, here, this is the example. For the gradient, first quantity is gradient. Now, part A is del V. Del V is partial V by partial X plus partial V by partial Y plus partial V by partial Z. You can see here that this V is a function of X, Y, Z. So that is why I use this formula, which is for Cartesian. Derivative of this with respect to X and remaining as it is. So it is 2 e power minus Z cosine 2x cosine hyperbolic y plus derivative with respect to y e power minus x z sine 2x same, and then cosine hyperbolic y has a derivative sine hyperbolic y plus derivative with respect to z e power negative z. So minus e power negative z sine 2x cosine hyperbolic y. So here it is nothing more than taking the partial derivatives once you have the formula. Part B, del u. Now, what is the del operator, say in the cylindrical coordinates? Here you see del operator in cylindrical coordinates. This one. Here. So this will be equal to partial u by partial rho a rho plus 1 over rho partial u by partial phi and then a phi, unit vector a phi, plus partial u by partial z and unit vector az. Okay. Now let us compute them. What is partial u by partial rho? 2 rho z as it is cosine 2 phi and then a rho. No. Yes, a rho. We are finding gradient a rho. Here is my mistake. Here is my mistake. A sub x plus partial v by partial y, a sub y plus partial v by partial z, a sub z. So this is equal to cosine hyperbolic y ax plus ay plus az plus 1 over rho and rho square. So it is rho derivative with respect to phi. Cosine 2 phi derivative is negative 2 sine 2 phi. So rho square and 1 over rho, cancel 1 row, so it is rho z, and cosine 2 phi has derivative negative 2 sine 2 phi, a phi, and now derivative with respect to z, 1. So rho square cosine 2 phi a z. This is for part B. Similarly, we can get the gradient for part C. Gradient. And the formula is given above there, del W. And that formula says it is partial W by partial R AR plus 1 over R partial W by partial R theta A sub theta plus 1 over R sine theta partial W by partial phi A phi. Now, here what I'm writing is the gradient for the scalar field in spherical coordinates, and you see here 10r sine square theta. So this is equal to derivative with respect to r is 10 sine square theta cosine phi ar plus derivative with respect to theta, and 1 over r will cancel that r, so it will be 10 multiply derivative with respect to theta is 2 sine theta, derivative of sine theta is cosine theta, and cosine phi same a theta plus 1 over r sine theta. So 1 over r sine theta will cancel r and 1 sine theta, so it will be 10, and then sine theta, r cancel, 1 sine theta cancel, so 10 and sine theta left, and derivative of cosine phi is negative sine phi a phi. So this is in short the gradient of scalar fields in Cartesian, cylindrical and spherical coordinates. So once these formulas are given, it is very easy for you to compute these partial derivatives, and what? And the gradient, that's it. Okay, so we have seen gradient, curl. Similarly, there are some other practice examples, 3.4, 3.5. Okay, example number 3.3 is this one. Practice exercise 3.3. You can do that in yourself. You can see example 3.4. A function w equal to x square y square plus xyz. Compute the gradient and the directional derivative. Okay, this is the application of the gradient. So let me write here. Directional derivative. Directional derivative of a scalar field of a function directional derivative of a function. What function? In x, y, z, in rho phi z, in r theta phi, whatever it is, of a scalar function. Let me say it a name. V is directional of a v, directional derivative of a scalar function v in the direction of a unit vector u hat is. One more thing. In the direction of a unit vector u hat, at some point, at the point capital P is directional derivative of v, and here u hat, it is equal to gradient of v at P, gradient of v at point P dot u hat. So this is the application of the gradient. Second application of the gradient, another application of the gradient is to find angle between two vectors. Okay. Note. Let me write this as a note. Gradient v is a vector normal to the surface. It is a vector which is normal to the surface. What surface? This v is a function of x, y, z. So you can say it depends in which coordinate system we are having this surface. So we can say that it is normal to the surface we are using this v, v to the surface v equal 0. Or there should be another new variable. So normal to the surface given by v. Okay, by example it will be more clear. Let me do one, say, example or practice problem. Here is the example. Okay, why I'm solving this example? simply do the examples given in your book. The solution is given. Solve the solved examples given in the book. They are very easy, very straightforward. Like here, what I just show you this one, Shabab. You see, finding the gradient. This is what? Very easy, very trivial thing, simply taking the derivatives when formula of this del operator is given to you, you have to take simple partial derivatives. And you have seen directional derivative in your calculus course, Math 201. You have seen these directional derivatives in Math 201. And also, even in Math 201, we tell to students that this gives us gradient is a vector which is perpendicular to the surface. So you do the solved examples. Divergence. Okay, what is application of divergence? Divergence. The divergence. Do you know, by the way, what is divergence? Shabab, someone tell me.
There are no solutions.
Divergence of a vector field. Okay, let me write a note here. Look, you know, divergence of a vector field. Divergence of a vector field is the tendency of the vector field to converge or diverge at a point. Like you see in figure A, this is a positive divergence, like a light bulb. So light is diverging from the bulb. And in part B, suppose light, it is these vectors, they present light. So it is converging to the point B. So in part B, it is converging. So it is a negative diverging. Converging means negative diverging. And in part C, you see there is no divergence. These vectors are not coming to a point or going away from a point. So it is zero divergence. This is what divergence mean.
Doctor,
Yes.
so when we solve for divergence equation, we only find one of these errors, maybe, or what?
Okay. If you have a vector, you find the divergence, you find all these vectors. But if you replace a point, certain point P, particular point P, then you will get one of these vectors. You get my point?
Yes, yes.
For example, if you replace x equal to 1, y equal to 2, z equal to 3. So you are now looking the divergence at a certain point. And that will be a vector because no, divergence will be a scalar quantity for a vector quantity. So divergence, you are looking at a point, not the vector. Yes, again, when you are looking for divergence, it will be a scalar quantity. If that quantity is a positive, it means, you know, divergence is del dot vector v. So if del dot vector v is positive, it means at some point P. Yani you find the divergence, replace x equal to something, y equal to something, z equal to something. So you are finding divergence at a point. If the final answer is positive, it means that at that point, the vector field is diverging. You find the divergence, replace point P, your answer is negative. It means at that point, the vector field is diverging. Converging, negative diverging. And if the answer is 0, because as I said before, divergence is a scalar quantity, divergence of a vector field, but it gives you a scalar quantity. If that scalar quantity is 0, so the vector field is neither converging nor diverging. For example, here, this is the gradient, sorry. And here you are seeing the divergence. And in the divergence on the right hand side, we have no unit vector. No unit vector here. Divergence is a scalar quantity. Divergence of a vector give us a scalar. Now, if that scalar is positive, divergence, negative, convergence. Yani negative divergence means convergence. 0, nothing. I hope I'm clear.
Yes, clear, doctor. Thank you.
Okay. Now, using this divergence, we have a theorem we will be using, and that is called divergence theorem. Let me write in red color. Divergence theorem. What is a divergence theorem? That we can evaluate a surface integral over a surface with closed boundary. You know, the left hand side of this, what I paste here, is integral over S. S is a surface, A dot ds, and what a small circle on the integral tell us? It tells us that the boundary of the surface is closed. And what is the right hand side is divergence A dv, is a triple integral like you do in same as in calculus. Triple integral same as we do in calculus. We do not do A dot ds in calculus 201, neither 102. 102 is a small course. So even in 201, we do not compute this left hand side. What we do is compute on right hand side. The right hand side is what? A triple integral. Shabab, just give me 1 second. Okay. This is a triple integral, same as in Math 201. And we will compute this. So this is the divergence theorem. You may have question about divergence theorem. You may have a question about finding the directional derivative. You may have question about finding the gradient, finding curl, finding divergence, finding Laplacian, computing these answers at some particular point, blah, blah, blah. So far here, you see, first one is directional derivative. That is application of the gradient. We have gradient V at point P, del V at P dot U hat. U hat is given a unit vector. And now this divergence theorem is application of the divergence. First application of gradient, then application of divergence. And we will solve questions related to this divergence, yani divergence theorem. Divergence theorem. Now there are other examples I'm seeing here, and one more thing is left. That is Stokes theorem. And Stokes theorem is using the next quantity, and that next quantity is a curl of a vector field. Curl of a vector field. There are several examples given here in the book. You must try to solve them. So let me also write this Stokes theorem. Stokes theorem is used to evaluate a line integral using surface integral. A line integral using surface integral. Okay, one can ask, Shabab, one can ask teacher, line integral, maybe it is easy than surface integral. Now look here, for example, if your curve is given like this one, then how many line integral you need to compute?
Three.
Three.
Like we did. And how many surface integral you need to compute bounded by these curves?
One.
Only one. Only one. So you will see that this Stokes theorem is also very helpful. Now here you need to notice, you need to let me say either notice or remember that if question is given that use Stokes theorem to evaluate this side, do you see the underline what I put?
Yes.
If question say use Stokes theorem to evaluate this line integral, you do not have to do the line integral. You have to compute the surface integral because this is the use of Stokes theorem. If you have to compute the line integral, why do we say use Stokes theorem? So if we say use Stokes theorem to evaluate this one, you have to evaluate the other side, whatever side is given. You evaluate the other side of this formula. Okay, this is very important thing. Now this is Stokes theorem. Now next we have seen divergence theorem, Stokes theorem, and we have seen directional derivative. There are several solved examples here to find the curl, to find divergence, to find the gradient. And formula will be given like I gave you, and I will give you formula in the midterm exam. I'll give you the formula. By the way, I uploaded a formula for this quiz in the course content area, and I sent you by announcement email. So you just download that formula. That is only for chapter 2, but I have in the exam, I will give you for chapter 3 also.
Doctor, does that mean the things that were not in the formula will be with us in the quiz?
In the quiz, you download that formula sheet, okay, and you can see that those formulas on your screen. But in the midterm exam, I will print the formula sheet and attach it with your question paper. Mazboot?
But I mean, doctor, in the formula you uploaded, there are some laws aren't included.
I
Like the
didn't understand
distance.
what you are saying. There are something not
some,
included.
yes, like the
Like what?
Some of the
The
theory, doctor,
distance
is not
law.
there, like the divergence theorem, stock theorem. Some of the question, other chapter 3 are, is it with us or not?
Look, that is for chapter 2 only, what I put on the blackboard.
Doctor, what about the distance between 2 points for the...
Okay, Shabab, you need to be smart. If I'm not putting a formula for something, what does this tell you?
It's not in the quiz.
You need to be smart. Don't ask everything clearly.
It's no brainer, doctor.
Okay. Now that formula sheet is only for chapter 2, but in the exam, I will give you formulas for chapter 3, which include gradient, divergence, curl, Laplacian, Stokes theorem, divergence theorem, directional derivative. Directional derivative may not be given because you have seen this in calculus, Math 201. So all these formulas, they will be given to you in the formula sheet, and that I will print. There are 2 pages of the formulas, which I will attach to your exam paper. Okay? Right, Shabab?
Doctor, I have a question about the chapters that you uploaded. I tried to find the answers on the internet, but I couldn't. So how can we practice? Could you upload the answers?
You mean answer of the exercise at the end?
Yes, doctor, please.
I don't have those answers. You can solve.
Do you have the book, doctor?
No, I got it from someone. I don't have the book actually. If I had, I should have given you even in the beginning. Okay, let us do. Oh, we have just 1 minute left. Shabab, this is my advice. All examples given in your book, practice exercises given in your book, examples given in your book, you must solve before you go to solve any question from the exercise. Because of what I'm seeing here, for example, example 3.9, it is a use of Stokes theorem. So this will tell you how to use the Stokes theorem. And example 3.8 is how to find curl in 3-coordinate system, Cartesian, spherical, cylindrical. Similarly, before that Stokes theorem is given, some these what are these any curl, divergence, blah blah blah, everything is given here in your book. It depends on you that how much practice do you do. For example, 3.7 determine the flux of G. And you know that the surface integral give you flux. So find this flux. Okay. And the solution is given here. Anything not clear, I'm here to help you. But the main thing is that you need to do these examples. And yes, when we finish all the theory, we will go to the exercise and do some